Good morning. Thank you everyone for being here. We're excited to be here. We're Boise State University. Our use case, obviously Pacific Northwest National Laboratory. We'll introduce our team here. We are comprised of mechanical and engineering undergraduates. Oh, not too far. There we go. We're comprised of electrical and mechanical engineering undergraduates. There's only going to be a handful of us present today. Myself, Andrew Kinney, Jake Fuller, Will Rendler, Glenn Taylor, and Azia. And we also wanted to acknowledge our mentors and advisors at the bottom and thank them for their support and help throughout this year. We'll cover the work distribution. We were split into 4 subgroups. We split them into a conceptual design team, a financial team, a distribution team, and a development team. We had weekly meetings to keep ourselves on task, and then bi-weekly meetings with our advisors and mentors. And we'll just jump into our solar plus storage design. We'll cover PNNL's needs. They obviously needed a system for resiliency. They wanted microgrids constructed to island their critical loads. So our design goals were to use the existing grid to define microgrids. And then we use those, we wanted to island those microgrids using smart grid equipment. That'll combat any outages or disruptions on the grid. And then another design goal was to supply enough energy to those critical loads from PV systems and battery storage systems that we designed. And then we'll also cover our panel placement and battery equipment placement and then our expected operations. So here's our campus overview. You can see in the red is outlined where we were able to place our equipment, our PV systems. And you can see that there's a pretty big gap between the north area and the south area. So we decided to split our microgrids into 2 systems. We'll have the north microgrid shown here. This is comprised of 2 buildings, or 331 and 318. In the event of an outage, these 2 buildings are going to be critical loads. And then we'll cover the south campus here. We'll have 6 buildings on the south campus, but only the EMSL 3400 and 3410 will be on critical loads in the event of an outage. And this is another figure of our north campus. You can see that we placed the PV system just west of building 331. And then we placed our battery storage system and equipment just south of that. We use these areas for the reason they are open fields, there's no obstructions, and there's really good irradiance there. And then our equipment is compact, close to the PV system, and also is very close to grid interconnection points. We'll cover the south campus. We had the same idea. This is just placed just south of the main loads on the south campus. PV system in the open fields, and the battery storage is right next to it. We also ground mounted our PV systems, and we use a tilt angle of 35 degrees. This angle helped us produce more energy in the winter. Rather than just maximizing our annual production, we wanted to make sure that we were able to provide enough energy in the worst case scenarios. We'll cover a quick equipment selection. We used a Helion 460 watt bifacial module. These put out really good power and they're very reliable. And then for our inverter, we used a smart inverter by SMA America. For our north campus, we used the Sunny Central 2200, and for the south campus, we used 2 of the 2750s.
All right, so going along with that, PNNL is located in Richland, Washington. They're just off the Columbia River, and their local utility supplier supplies very cost-effective power. It's pretty cheap. So when we were designing our system, originally we entertained the idea of peak shaving, some cost-saving strategies, and we found that by optimizing our system to include these things, we just weren't saving PNNL any money. The utilities power was too cheap, and so we switched our focus and focused on resiliency instead. And so we did not optimize for peak shaving. So going off of that resiliency theme, PNNL had specified critical loads and also asked us to guarantee those loads for specific ride-through times. So when we were sizing our batteries, we took the critical load and the peak load for our energy, and then we use the peak load and then the required ride through time to get our kilowatt hour energy size. And then we used system SAM to model both of our systems and use that for our loss calculations. And so we added some loss provisions for losses in there in our battery sizing for both the North and the South campus. So again, just in general, the solar arrays, our PV arrays, were sized so that they could recharge our battery anytime throughout the year. So worst case scenario, it's winter time, there's an outage, power gets restored, and then a day or two later, there's another outage. We wanted to make sure that our PVs could recharge our batteries in sufficient time so that they'd be available to, again, provide that resiliency. Total North Campus system size is 2.36 megawatts, annual production of 4.22 gigawatt hours, and the battery size is 4.62 megawatt hours. South Campus is a 9.02 megawatt system, annual production of 16.1 gigawatt hours, and a battery size of 15.6 megawatt hours. So again, we designed this for resiliency. However, we did have two very big batteries just sitting there with a bunch of energy in them. And so since our system was designed to recharge them during the winter, we do have some extra production, not over the load, but we do have more production than we need to recharge the batteries during the summer. So we wanted to make use of some of this energy that's just sitting there. So even though it was not an optimized peak shaving algorithm, we did design a discharge algorithm that would discharge the batteries during the summer months when we have enough energy in the system to discharge the batteries, but still ensure that the critical loads would be covered during an outage, and also ensure that the batteries would be recharged before the sun went down, so that those batteries would be available if an outage happened at night. As far as resiliency goes, we use SAM to model and test resiliency. We use the new function of SAM to actually model exactly what would happen during an outage. We simulated outages once a week for the entire year during various times during the day. At night, we simulated it at midnight because we figured if it was dark, it was dark. So there wouldn't be a real difference there. But during the day, there were at various times throughout the day. You can see that both North and South Campus, we can guarantee that the critical loads will be covered throughout the year with our system. This is a very simple diagram of kind of explaining what would happen during an outage. So during an outage, we have our monitoring software, our PTs and our CTs, detect that the grid was down, close the breaker, and island our system, P&L system from the main grid. Then we have the real-time automation control, or RTech, that would work with the reclosers to close out non-critical loads, so that we would only be supplying the loads to supplying power to those critical loads. And then the microgrid controller combined with our smart inverters would establish stability to make sure that there's stable power to the critical loads. Once the system detects that the grid is back on, it would work to reconnect and then re-bring those non-critical loads back online. As far as distribution goes, there's several things we have to worry about, especially with solar. We're worried about over voltage and reverse power flow. Some of the things that we did in our system to mitigate this was we used power curtailment and ensured that the system produced less than the load demanded. So we have enough to cover critical loads, but our system does not supply the full load all the time. And also, we made sure that our system was close to where those loads were. And we also, our smart grid components help also reduce that risk, our inverters. And then during an outage, our microgrid controller also ensures stable power.
So to create the financial model, we had to make a few assumptions, some given by the SDC. A few being the property tax is 0 over the course of the PPA lease. The corporate tax rate is 27% for state and federal combined. The construction timeline is about 8 months. The PPA lifetime is 20 years and the PV lifetime is 30, along with inflation is 2% over per year. So for the system cost breakdown, the South Campus came to an approximate $19.7 million total cost with a negative 0.55% cash on cash IRR. That resulted in a PPA price being set at 6.59 cents per kilowatt hour. And for the North Campus, a $6.3 million total cost with a 2.97 cash on cash IRR over the course of the 20 years. And that resulted with a PPA price being set at 12.24 cents per kilowatt hour. This brings our entire system cost to $25.9 million. For their customer savings, we use Energy Toolbase to do the analysis. The main takeaways here are the net costs of the systems being $6.78 million and $1.96 million for the South and North Campus respectively.
So as outlined in our conceptual design, our build areas are out in these red areas on this diagram. And according to the PNNL 2017 master plan, these areas are good to build and have no future developments planned for them. So in terms of zoning, the PNNL is located, North Campus is located in Benton County, Washington, and is zoned as light industrial. And then the South Campus is located in Richland, Washington, and zoned as a building research park. PNNL is a government entity, so they are their own authority having jurisdiction. So in terms of code compliance, PNNL is exempt from local and state codes. They have to follow federal codes, however, but it is the best measure to make sure that they're following some of the local codes as well, to make sure that any developments would blend in with the existing ones. In terms of batteries or energy storage systems, these are restricted by the NFPA 855 document. And from that, we are able to, or our batteries in this case are considered remote ESS. And this allows us to have larger capacity and less restriction. And all of our components must abide by the Buy American Act as well, because it's a government construction operation. In terms of staging, we want to make sure that all of our materials are going to be safe in terms of theft and also just out of inclement weather. So covered up by tarps if they're non-sensitive, but also inside locked shipping containers, which are watertight. In terms of staging, this is a quick diagram. But basically, we go from orange to yellow, and we go from the staging area to the construction area, and we use the adjacent lots for staging. And this is both for the South and North Campus too. So we have this for the North Campus as well.
So a few potential risks noted that may hinder the deployment success would be weather. PNNL is very rainy, so it's important, as mentioned before, to store the materials in shipping containers or to cover them with tarp. Security is another issue. Although it is rural and a low crime area, we should consider this, and we're going to put fencing around the job site and make sure the shipping containers lock. Staging is important as well. We need to stagger the material shipments to limit the possibility of theft and damage. Scheduling delays can always happen, so it's important to have clear communication with suppliers to prevent any supply chain issues that may happen, as well as finding backup contractors to make sure that the project's not delayed due to labor shortages. Materials can break when they're shipped or on site, so at the end of each day, workers should assess and log any changes of materials that may have been broken. This is a summary of our Gantt chart, assuming ideal circumstances and that the needed materials are readily available. Our project timeline is roughly 11 months. And an important thing to note from this is that the construction of both the South and North Campus solar arrays will take roughly 8 months. So achieving community engagement, the main community members affected by this project are PNNL employees, surrounding businesses, as well as local residents, farmers, government, and nearby schools. Our strategy to engage these members include aesthetic landscaping around the panels. Pictured to the right, we are going to be placing tall fescue sod under all the solar panels and around the perimeter of each of each area, we are going to be placing Pacific Bleeding Heart and Satan's Devil, and as well as a 6-foot chain link fence. Another way to engage these members, we're going to post flyers and signs around the campus to outline the system benefits, which are cleaner energy, better resiliency, and less demand on the grid. Thank you for your time. Do you have any questions for us?